Hey, welcome back. This is Calc 2 now. So if you took my last class, guess what? We're going to do 5.7, 5.8, 5.9 again, just in case we have some transfer students. We need to cover all of our bases. Let me make sure I'm recording here before I get too carried away. Are you? Yes, okay. Okay, so let me get rid of this. Okay, so 5.7, the natural log function again, integrating the thing. We'll sort of begin here with the, okay, so I'm not plugged in, I apologize. There we go. Okay, sorry about that. And of course, Q the cat is going to start meowing at me as soon as I get started. Right, so the rule, so for all of these integrals, we've had all kinds of rules to follow that you basically just have to have memorized. But the rule for this section is as follows. You'll have the integral of something like 1 over x dx, okay, which of course can be written in all kinds of different forms, which can be confusing. You could write dx over x, you could write x to the negative 1 dx, etc. Anyways, the rule is to write then ln of the absolute value of x plus c. And we could kind of get there later here in the next section when we deal with inverse functions by kind of implicitly differentiating. So if you had f of x basically equaling e to the x, and then you have f inverse of x equaling the natural log of x, then you could say, well, okay, f of f inverse of x, the composite of that would just equal x. And then you could take the derivative on both sides implicitly, so you'd have f prime of f inverse of x times the derivative of the guts. And then that would equal, I guess like that, getting carried away with the parentheses, that would equal 1. And then you could solve for the derivative of the natural log. And then from there we can get the, the integral, sort of. So f inverse prime of x will equal 1 all over f prime of f inverse of x. And then, what is f prime? F prime comes from here. So we know the derivative e to the x is just e to the x. And then we can substitute that in there. So it's 1 all over e to the f inverse of x. And of course, f inverse of x is just the natural log of x. And the e to the ln of x is just x. Okay. So if the derivative is 1 over x, then the integral is the ln of x. Right? So if the derivative with respect to x of ln of x is equal to 1 over x, then the integral of ln of x, the integral of 1 over x, the integral of 1 over x dx is kind of, right, the natural log of the absolute value of x. We're going to sort of slip that in there on you. Truth be told, if you remember from Calc 1, the derivative of the natural log of the absolute value of x is 1 over x. And that will allow us to kind of expand the intervals on which we can play with this antiderivative. So later on, there's questions about the sort of domain of the original function and then its derivative, and we deal with issues like that. Okay, so what? That was a lot of fanfare for very little. This is what you need to remember. Clearly, you need to have this memorized. This other stuff, I guess, kind of got carried away there, sorry. Okay, so anyways, let's look at some examples, and kind of the craziness that's going on. So the integral of something like 1 all over 5x dx, right? So you can factor out the constant 1/5, and then you get 1 over x dx, and then that's sort of our integral of the day. So you get 1/5 ln of the absolute value of x plus c, right? The book does it in a different way, so you may remember me already talking about this, of course. You could do a u sub, right? So if something is not in the form of 1 over x, usually you can do some sort of, well, in this section you can do some sort of u sub to put it into that form, and then it becomes a natural log. So you could also do a u sub on this guy, right? It's a bit silly because it's going to be a little bit longer. So let u equal the 5x. And then if you're not seeing how I do my u subs, this may be a little different. It's fairly simple though. I just call u whatever I want it to do the simplification, and then I solve for dx. Okay, so you can divide. Here I have the differential of u. I just took the derivative of 5x is 5, and then dx. Then solve for dx by dividing both sides by 5, and you get dx equals du over 5. And then what I do is substitution. Usually I just do this and this and the integral. So it'll be 1 all over u times dx, which is now du over 5. And then that'll equal, you can factor out the 1/5, you get the integral 1 over u du. Then you could apply the integral rule here. So this would be the ln of the absolute value of u plus c. And then you back sub, right? So you get 1/5 ln absolute value of 5x plus c. Okay, so you're looking at these two things, and they're clearly kind of different. Okay, you can make them look more similar by using rules of natural logs. You could say this is 1/5 ln absolute value of 5 plus ln absolute value of x, okay, plus c. And then you can distribute the 1/5, and you get 1/5 ln absolute value 5 plus 1/5 ln absolute value of x plus c. And now it looks a bit more familiar. So both answers have this thing in them. Okay. So are they the same answer, or are they different? They're the same answer. If you recall, these answers represent not just one curve, but rather a family of curves. So if you were to draw out 1/5 ln of x, and then 1/5 ln of x plus 1, and then 1/5 ln x plus 2, you would end up with this sort of picture. Okay. What you're seeing, the variable part, is kind of the generator part. Okay. And then you have this plus c. Okay, so this that I just circled in red is going to be one particular curve out of the bunch. Okay. When I have this 1/5 ln 5 plus 1/5 ln of x, that's a different sort of generator curve. Maybe that's a little higher, right? So maybe that's this guy right here. It doesn't matter though, because if all you're doing is kind of finding a starting place. Okay. What we usually do is just take that 1/5 ln absolute value of 5 and put it into the constant part. So you could rewrite your answer as 1/5 ln absolute value of x plus c. So I use this kind of how do I explain it? Usually I use chess. So if you've never played chess, please go out and buy a chessboard. It's a lot of fun. Anyways, imagine you have a simplified chessboard, right? And you want to kind of draw all the positions the rook can get into. And we'll start the rook right here. Okay, so where can the rook go from that position? Well, he can go right here, And then from there he can go 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 here, and then he can go here, and then he could go here. But that's it, right? Those are all the different places it can move. So this picture here is kind of like the family of positions that you can get to from this one space. Okay, so then let's look at starting from a different place, right? So same kind of idea, but this time we'll put the rook somewhere else. I'll put the rook right here. Okay. So that's like the starting place, right? So from there, the rook can go here, and then from there he can go here, and then from there he can go here, and then here, and then here, and then here, and then here. But he can't get anywhere else, right? He's never going to get to that middle square. Okay. Look, the pictures are the same, right? At the end of the day, the sort of quote-unquote family of positions the rook can get to is exactly the same. And that's kind of what we're getting at with the red answer versus the blue answer, right? So the red answer is kind of like starting in the bottom corner and then going everywhere else. And then the blue answer is like starting on the right at this middle position here and then going everywhere else. In either case, it doesn't really matter because you're going to get to all the other positions, right? So they're kind of the same answer. And just to make things easier, we kind of have this one kind of good answer, which is where we take this 1/5 ln5 and plop it into the constant. So you just are, they're the same. Okay. In general, when you're simplifying these things, what you're going to do is take that constant part and so this part is a constant number, right? It's 1/5 ln5. You're going to let it get absorbed into the constant. So all non-variable parts get absorbed by this constant of integration. And so long story short, yeah, they are the same answer. Even though they look different, you get the same answer. And we can even go into one of our favorite kind of integrators and see if we get the same answer, right? So a lot of AI stuff out there to help us through the day. I know a lot of students use this for homework. If you use it on a test, you're going to be in a lot of trouble. So let me just state that now. And usually I can tell because your answer will look exactly like the Mathway answer. You won't make any mistakes besides just copying it down wrong. So please, please, please do not do that. So anyways, let's look at what Mathway gives us for the answers. Is it going to give us the same answer, or is it going to give us these two different answers? Which answer? So it gives us the answer by absorbing the plus C in there. Let's see if it gives any more options. No, not really. So Mathway gives you the traditional answer. Are there any other solvers? So Symbolab. Let's see what they give us. Integral 1 all over 5x dx. Yeah, and they're giving us the same answer. Let's see what Wolfram does. Wolfram alpha. And may have to, I think they have a keyboard here where you can write it in, but I usually don't use it. Integral of 1 over, yeah, I don't like that. So I'm just going to type it in the code. Integral of 1 over x, comma x. Oh, it's 1 over 5x, sorry. 5x, comma x, and then push enter, see what it does. Oh, and it gives us something that looks really weird. The weird thing about Wolfram is the natural log is kind of in the Wolfram computing language, it could be written as regular logs somehow. I don't know why, but so it's interesting to look at what the different calculators give you as an answer. Sometimes I can tell students are cheating just by that. So in this case, if you wrote log of x over 5 plus, and you literally wrote out constant, then I'm going to have some issues with your test. I'll probably give you a 0. Okay. Is very unhappy with what I'm doing, but there it is. So let's get back to work, right? Okay, so that's sorry, got a little sidetracked there. Okay, let's look at some other problems. So I'm just going to pick some maybe out of the book here. Here's number 5. Integral of 1 all over 2x plus 5 dx. And this is going to require a u-sub. So u-subs generally, you know they work if it reduces the number of variables, the number of literal symbols in the integral. And you always have to get rid of the x material as well. So you can't have this weird multivariable integral resulting with u's and x's. No. Okay, so if we do a u-sub for the denominator, I think that'll sort of do the job. So du is going to be 2 dx, and I like to solve for the differential, divide both sides by 2, and then do all my substitutions. So this will be the integral of 1 all over u times dx, which is now du over 2. I could factor out the 1/2, integral of 1 over u du, and then have 1/2 ln absolute value of u plus c, and then back substitute. So you get 1/2 ln absolute value of 2x plus 5 plus c. Okay. Let's see what else. Oh, these area problems. So one of the applications of integrals is just literally finding area of regions. So let's take a look at one of these problems. So let's try number 80. So we have the integral, oh, whoops, they don't set it up that way. They say, find the area of the region bounded by the graphs of the equations, use a graphing utility to verify your results. So we have y equals x plus 6 over x, and then line x equals 1, line x equals 5, and the line y equals 0. Okay. Graph it. This thing right here, if you rewrite it, x over x plus 6 over x, that's going to equal 1 plus 6 over x. So it's just a shifted version of this thing, right? This rational function, 1 over x. So that's a graph of 1 over x. Not a very good graph, but there it is. And this 1 is going to shift it up by 1, right? So it's going to move the asymptote from y equals 0 to y equals 1, right? So we're going to have this kind of picture going on. Okay. Whoops. The vertical asymptote there. Okay. X equals 1 is a vertical line at 1. X equals 5, 2, 3, 4, 5 is a vertical line at 5. And then y equals 0 is the x-axis. So the region we're trying to find the area of is this green region right here. And of course we could do that with an integral. That's what integrals were kind of originally defined as for us. Originally we did them as antiderivatives, right? And then we defined them as area underneath the curve. So this would end up being the integral of x plus 6 over x, but we're going to rewrite that as 1 plus 6 over x dx. And then we need to integrate from 1 to 5. Okay, so a definite integral. Okay, so first find the antiderivative. Integral of 1 is x, and then plus this other integral. This would end up being, x plus the integral of 6 over x dx, and then you could factor out the 6, integral of 1 over x dx, and then that integral of 1 over x, of course, is the natural log of the absolute value of x, and then we have to evaluate from 1 to 5. Okay, So substitute in 5 first into the antiderivative. You get 5 plus 6 ln. Absolute value of 5 is just 5, so 6 ln 5. And then minus, now substitute 1 into the antiderivative. So you have 1 plus 6 ln of 1. Absolute value of 1 is just 1, so ln of 1. The ln of 1 is 0. So I'll have 5, eventually minus 1 is 4, plus 6 ln 5, and you get an approximation with your calculator. I won't bother you with that. Okay. There's always these weird, tricky ones where it kind of doesn't maybe even look like it's a natural log problem, but it turns out to be. Let me find one of those here in the book. Where are you? I'm trying to not do the same problems I did last year, so that's kind of my issue right now. Oh, here's one. We have the integral of, okay, so number 10, let's put this guy. So the integral of x squared minus 2x, and this is the quiz question for section 5.7. This is the quiz question. You need to write it on a piece of paper. I'd prefer if you turned in 4 quiz questions at once. So you'll for the first video quiz submission, you'll turn in this problem from 5.7. You'll turn in one problem from 5.8, one problem from 5.9, and one problem from 6.1. So on a piece of paper, you're going to write out these problems and the answers, just like I'm doing them here, and then you'll take a picture of them, upload them to your computer, convert them to PDF, and then submit them in Blackboard through the email system. Okay, so x squared minus 2x all over x cubed minus 3x squared dx. Okay. So the deal with this guy is, well, first off, you can reduce it a little bit. Okay, you can factor an x out of the top and bottom. So maybe that will help a little. So I have x minus 2 all over x times x squared minus 3x, sorry. Okay, dx. So, okay, yeah, that's great. Then we have the integral of x minus 2 all over x squared minus 3x dx. You can this isn't the kind of problem I was really interested in, of course. We'll do it anyways. At this point, then you can simplify it a bit. Geez, that's not going to work. I apologize. This is your quiz question, huh? Yeah. So let's see what happens if we do a u sub for the denominator first off. Minus 3x squared. So du equals 3x squared minus 6x dx. Okay. I think this is going to work. Okay, so dx equals du all over 3x squared minus 6x. It doesn't look like it's going to work, but it will, because if you factor out a 3 from that denominator there, it's going to pan out for us. So we have the integral of x squared minus 2x all over u times du all over, and I'm going to factor this this part of it when I do my substitution here. So I'm going to bring out a 3, and I'll end up with what? Guess what? X squared minus 2x, right? So lo and behold, we have this nice cancellation between the x squared minus 2x and the denominator and numerator. Okay, so there we go. So this will equal the integral of du over u, which will equal the natural log of the absolute value of u, which we need to do a back sub then. You get the ln of the absolute value of x cubed minus 3x squared plus c. Okay, so you just have to turn it in. You know, obviously you won't do the scribbling part, but that's the question for the quiz. The first question of the 4 questions I want you to turn in on the first video quiz submission. Okay, thank you. Let's move on. There's long division problems, of course. So like number 15, let's take a look at that guy. You have to remember how to do polynomial division. X squared minus 3x plus 2 all over x plus 1 dx. So we have x squared minus 3x plus 2 divided by x plus 1. So how many times does x go in the x squared? So x, right? X times x is x squared. So we have x squared plus x times 1 is x, and then you have to subtract. Okay? You may have to look back to an algebra book, or maybe look up some videos on polynomial division if you've forgotten how to do this. So x squared minus x squared is 0. Negative 3x minus x is negative 4x. Bring down the 2. Then what times x is negative 4x? Well, negative 4. So we have negative 4x, then minus 4, and then we have to subtract this, and we get negative 4 is positive 4, so 6. And that right there allows us to rewrite the integral. Okay? So you could rewrite the integral as, and the way you always do this is kind of a counterclockwise or a clockwise motion, x minus 4 plus 6 all over x plus 1. Okay, so we get x minus 4 plus 6 all over x plus 1 dx. And then integrate. So the first two terms we can integrate is x squared over 2 minus 4x. And then we can factor out the 6 from this last guy. So I just looked at the parts as integrals. The integral of a sum is equal to the sum of the integrals. Okay. You really don't need a u sub on this one. Okay, so you could do a u sub for x plus 1 if you wanted, but you're not going to have any constants floating about because du is just going to be dx. Okay, I'll write it out so you can see it if you don't see it. X squared over 2 minus 4x plus 6 integral of 1 over u, and then dx is just du. And then you end up with x squared over 2 minus 4x plus 6 ln absolute value of u plus c. And then you could back substitute. So you get x squared over 2 minus 4x plus 6 ln absolute value of x plus 1. Okay, so there it is. Just a reminder, with these videos, you can fast forward the videos. You can play the videos slow. So there's actually like a button on there where you can slow down the video, you can speed up the video, anything you need to do to keep your sanity, by all means. Okay, let's look at another type of problem. Look at, I guess, example 6, right? So this one's a little weird because the u sub doesn't quite do the job, right? I think it was example 6 in the book. It may have changed with the newer editions. But anyways, it's an important problem, and we want to take a look. Okay, so you try to do your u sub, probably x plus 1, right? So you have u is x plus 1. Du, the differential, is just going to be, well, the derivative of x is 1, the derivative of 1 is 0, so it's just 1 dx. And you try to do your u sub, but it doesn't get rid of the x in the numerator, right? So you have 2x all over u squared du. And that's a no-go, right? So either you have to do a different u sub, or in this case, you can actually play around with your original substitution. Right, so you're going to take this original substitution as an equation and just solve for x. So if you subtract 1 from both sides, you'll end up with x equals u minus 1, and that turns out to do the trick. Okay, so you can rewrite x and the integrand as u minus 1. That's all over u squared. And then you could distribute the 2, and you get 2u minus 2 all over u squared. And then you could bifurcate it, or butterfly it. Some people say fillet it. Okay, so you get 2u over u squared minus 2 all over u squared. And then, of course, we want to go ahead and simplify. This first guy is a natural log. The second guy we're going to do a power rule on. Right, so again, the first guy is just going to end up being 2 ln absolute value of u, and then minus 2u, so add 1 to the old exponent. Negative 2 plus 1 is negative 1. And then multiply by the reciprocal of the exponent. So that'd be 1 over negative 1. Okay, and then plus c. This will be 2 ln. I need to start back subbing. So u is equal to x plus 1. We have a negative situation. That'll be plus 2. And then u is again x plus 1 to negative 1 plus c. And generally, we hate to see those negative exponents as teachers. So you can always tell if you're dealing with a teacher because they will rewrite it as 2 over x plus 1. Okay, so there's that, right? Okay, let's look at one with a natural log floating around inside the actual integral itself. So this will be 21, or it used to be 21 in the book. All the numbers are off because they have to, you know, the game. The publisher moves all of the problems over by 1. I pretend like that makes it a new book. All I need are the questions. I don't really need the book at this point. But anyways, here we are. So ln of x, you know, is going to be our substitution. If you don't see it, you have to play around with it maybe. I'm going to let u equal to ln of x. And then du, of course, is 1 over x dx. And then solving for dx will give you x du. So replace ln of x with u. I get u squared all over x. And then dx is x du. So we eliminate the x variable. Those will divide out. And it looks like we have a simple integral u squared du. It's barely, not really even a log problem. I don't know, it's kind of tricky. They're trying to trick you. Okay, they're really making you earn a living here. All right, so back substitute, and for u, we have ln of x cubed all over 3 plus c. Wow, all right, good. Okay, let's move into then maybe some trig functions, some trig integrals. Wow, where am I? So I'm on section 2 now. So the great thing about natural logs, now we can pretty much handle all of the other traditional trig integrals. So you know how to do the integral of cosine x dx. That's just sine x plus c. You know how to do the integral of sine x dx. That's going to be a negative cosine x plus c. But you didn't know how to do the integral of tan x dx, and as well as the integral of secant. You knew how to do the integral of secant squared. All right, the integral of secant squared x dx was tan x plus c. But you didn't know how to do this one. And you didn't know how to do integral of secant x dx or any of the other ones, integral of cosecant x dx or the integral of cotan x dx. These were all giant mysteries for the Calc 1 student. I'm sure you lost a lot of sleep over this, right? My God, what is the integral of cotan x? No one knows. Right. Okay, so now with natural logs, we can finally answer these questions. For example, the integral of cotan, right? So the integral of cotan, let's make it a little more complicated, right? Of something, theta over 3, d theta. Okay. So if you didn't know what you're doing, you could always rewrite the cotan as cosine over sine, right? So you could rewrite this as cosine of theta over 3 all over sine of theta over 3 d theta. And then you could do a u sub for the denominator, now that we know how to do these types of problems. The differential will be cosine of theta over 3, and then the chain rule we have to multiply by 1/3, the derivative of theta over 3. Multiply both sides, or divide both sides to get d theta by itself, and you end up with 3 over cosine of theta over 3 du. So we can go ahead and do our substitution. Just the integral of cosine of theta over 3 all over u times d theta, which is 3 over cosine of theta over 3 du. And then we can remove these characters, and we have a nice little integral, right? So we have the integral, we can factor out 3, 1 over u du, and then that will be, did I screw something up? No, I didn't. Okay. So that will be 3 ln absolute value of u plus c, and then back sub 3 ln absolute value of sine of theta over 3 plus c. Okay. Okay. So yeah, in general, you should have that tangent one memorized. So the integral of tan of theta d theta, if you go through the same process, it's a little bit different. You'll end up with the negative ln of the absolute value of cosine theta plus c, which you could also rewrite if you think of this negative in front as -1. You could rewrite this using natural log rules, power rules, right? So you could bring this -1 as an exponent inside the natural log, and what that does is gives you, well, cosine of theta to the -1 plus c, and that gives you the ln of 1 all over the absolute value of cosine theta, which is the same as the absolute value of 1 over cosine theta plus c. Okay. And then 1 over cosine theta, if you remember all your little identities, your quotient identities, which I expect you do, is secant. Okay, so you'll see one of these two answers are both the same. Again, a lot of that going on. A big problem used to be in computer science was just figuring out if two answers are the same thing. So that, I guess, for a long time, or I think it was like an equivalence to 0 problem. Are these things both equal to 0? I don't know. Anyways, there's the secant problem. The integral of secant is a little more complicated, and it's not something you could kind of intuitively figure out unless you're super duper clever. I forget what problem this is. Let's just call it an example. We have the integral of secant theta d theta. How the heck do we do this? You can't really rewrite it and then do a u substitution. It won't work out. So the clever trick is to multiply secant theta over 1, top and bottom, by secant theta plus tan theta. And that seems to do the trick. So if we rewrite that, then we'll have, through our distribution, secant squared theta plus secant theta tan theta all over secant theta plus tan theta. And now if you're super familiar with your trig derivatives, you should see it, right? The derivative of the denominator is the numerator. So if we let u equal secant theta plus tan theta, the differential will be the derivative of secant is secant tan. The derivative of tan is secant squared. And there you have it, right? We can go through the rigmarole. So you don't need to do this, but I do it just because I don't know why. Plus secant squared today. So I plug all that material into my integral, secant squared theta. It's a lot of writing. Secant theta, tan theta, all over u times du, all over secant squared theta plus secant theta tan theta, just rewriting that using the commutative rule of algebra of addition. Then we have that nice cancellation, goodbye, goodbye. And then we have the integral of du over u, and that'll be the ln of the absolute value of u, and then you have the backside. So the ln of the absolute value of secant theta plus tan theta plus c. Okay, so right, I wouldn't expect you to have this one memorized. Some teachers do, you know, some teachers are just that cruel. They're listed in the book. You should probably have some sort of, I probably am going to force the honor students to be a little more careful about this than you, but the ln of secant theta plus tan theta that antiderivative is given in the book, so you can look it up whenever you need to. Okay. So they should have a chart of the integrals of the 6 basic trig functions. Okay, so I wouldn't expect you to have that one memorized, but you better have the tan guy memorized. So memorize either this one or this one. I don't care which. I have them all memorized. Okay, so anyways, let's move on. Is there anything else we want to do? Just a couple generic, and then I'll look at on Webassign and see if there's anything challenging that I need to give you a heads up about. Let's look at 39. The integral of secant x tan x all over secant x minus 1 dx. Okay, so clearly I think it's a good idea to go ahead and do the denominator. That's kind of when in Rome. The differential is the derivative of secant is secant tan. So you see that's in the numerator there. So cancellation minus 1, the derivative of 1 is 0, so it's just secant x tan x dx. So dx is du over secant x tan x. And then we do our subs. Times dx, which is now du over secant x tan x. Boom, boom. Du over u. So ln absolute value of u. C. So that's ln absolute value of secant x minus 1 plus c. Okay, great. Hey, let's look in on Webassign and see what kind of nonsense they have waiting for us. Let's look at, are there any ones we have to evaluate? Yeah, sure. All right, there's one we have to evaluate. Move this over here. Get rid of this jungle. Oh, there it is. Okay, so this is number 12 in Webassign. Integral from 0 to 6 and 9 all over 8x plus 1 dx. So we have u sub in order. 8x plus 1 du is 8 dx. Dx is du over 8. For these definite integrals with a u sub, I like to just drop the bounds and put them back in at the end. So I have 9 over u du. And I can factor out the 9 over u du. And then I can integrate. And absolute value of u, remind myself to evaluate. I can't evaluate until I back sub, because the limits on the integral are in terms of x. So the ln, the absolute value of 8x plus 1. And now I can put the, what the heck? It's already logging me out. Okay, so I need to evaluate from 0 to 6. So this will be 9 ln of the absolute value of 8 times 6 is 48, plus 1 is 9, 49, minus 9 ln of 8 times 0 is 0, plus 1 is 1. And of course, 9 ln of 1 is just 0. So I'll have 9 ln absolute value of 49 is 49. And then you go to your calculator dependent. Yeah, they want you to round the answer, so you just get a 3 decimal approximation. So that seems easy enough. It's one of those area problems. Let's try this guy. Looks kind of crazy, right? So we have number 11. Integral of e to the negative 8x tan of e to the negative 8x, excuse me, dx. And I want to do a u sub. So it looks like the u sub part is this thing. It's usually the thing on the inside of the function. It's like the guts. All right, so u is e to the negative 8x. The derivative of e to the negative 8x is e to the negative 8x right back at you. And then times the derivative of the exponent, which is the negative 8 dx. Solve for dx. So dx is negative du all over 8 e to the negative 8x. And then I can do my substitutions and still on e to the negative 8x tan of u times negative du over 8e to the negative 8x. We can factor out a negative 1/8. The e to the negative 8x stuff is going away. And we have the integral of tan u du. Okay? And then from above, the integral of tan u is the natural log of the absolute value of secant of u. Let's see, and then we can back sub. So this would be negative 1/8 ln absolute value of secant of e to the negative 8x absolute value plus c. Okay, so that's the idea. Hopefully that there's not a lot of I didn't put a lot of problems in Webassign. You know, do these problems or kind of a heads up, and then when we get back to the test, I'll give you a sort of pool of questions from the textbook that you can use for practice. But this isn't. If you think 12 problems is going to be enough to kind of make you fluent in this type of integration, you are wrong. I just want to remind you guys, before these, my first job was actually doing grading as a grader, and this was before they had these computer homework systems. So in those days, they would hire people like me to sit there and grade hundreds and hundreds of integrals from students. So that was my first job at the University of Akron, was grading, you know, from 2 to 3 sections of Calc 2. And I would literally grade hundreds of problems a night. So I got to be pretty good at integrals. It's not something that you can really put on your resume unless you become a teacher. And the truth is, the computers do it for us now anyways. But I don't know what I'm trying to say. I'm trying to say that if you want to become fluent in integration, it takes a lot more than just these 13, 14 problems. You're going to have to do a lot more practice. Okay, so once you get done with these, you have some extra time. You know, I always put my calc book where I can see it. So on a little pedestal, and anytime I walk by it, I do a couple calc problems. Do a problem before bed. It kind of embeds it in your brain while you sleep, that sort of thing. So anyways, that's it. That's welcome to Calc 2, you know, and thanks for watching. I assigned the quiz question for this video in the lecture, so you're going to have to find it, hopefully by watching the video. Okay, so thanks for watching, and we'll see you next time.